This is a companion video for exercise 12 of architectural simulations. This week we are learning a workflow to make a preliminary decision or decisions about an HVAC system and then size it for our building at whatever stage we are in design. The idea is really it's probably a schematic design level. Why would you want to know this already? Well, if you have a 20-story building that has a specific FAR and some cap on the height, you need to know your floor-to-floor ceiling heights, for example, very early in the project, or you may design something that doesn't meet the requirements of your client, like you can't get enough floors in there and you have to do a bunch of value engineering or reverse engineering to make it work. So this is a very straightforward, simple approach to getting a quick sizing and making basic decisions about HVAC early on. We're using for this a script that was developed by Ali Irani at MIT for this purpose. It's laid out like as an assignment. So basically, what this assignment says is what we're doing, but not exactly. Um, and I should say that this is a script, a Grasshopper script that is tied into Climate Studio. So we're going to be using Climate Studio zones and window material settings. So it ties in really well with what we've been doing this semester. I have a model here that you'll recognize probably because this is the medium office building that we've used various times in the semester. It's a 125 foot by 125 foot building, about 40 feet tall, 3 stories. And so I have a bunch of zones defined for this and have run thermal model or thermal analysis simulations in Climate Studio with it. So now we're going to use it for the purposes of this exercise. So the first thing we have to do, as always, is select a climate file. In this case, we're searching in the Climate Studio library. You, of course, could go, if you had a file somewhere else, you could access it there, but I'll just put in, oops, we'll use LaGuardia. So here's the path of LaGuardia. Climate Zone 4 is accurate for New York City. And now I need to bring in my zone geometry. So I'm going to select my zones here, select those objects, and set them as multiple B-reps in this component. Takes a minute, and you see now that it's been populated. And now I'm going to select a zone template for. So now I've hit this component, and now I'm in the Climate Studio library. Let's go ahead and pick. I'll just go up here to the top, and we'll pick an office, medium office from the basic Climate Studio templates. Next, I need to select my glazing. Here I have just a bunch of curtain walls, so I'm going to select those layers or that geometry and apply it or set it those B-reps to this component. And once again, I am going to go into now I'm in the glazing material database in Climate Studio. Whatever, I'm just going to leave whatever is in there right now because this is just an example, obviously. Next thing I have to do is set the ground plane or the ground. So because remember that we're, of course, air is different than ground thermally, so we need to identify where we're hitting the ground. I will set that B-rep in its ground. And we could add shading. So if I had, and you should do this if you were doing this for an actual project, if I had a context site here, so if I had a building here on the south side, all right, I had a little troubleshooting to do there. I had a clipping plane on that I didn't realize. So if I had a context building or a site here, I would want to identify this as surfaces or at least this. Let me explode this. I might want to make this then a shading surface so that that would play into my thermal model. And then, um, so anyway, I'm sorry. What we've done is select our geometry, uh, um, select our windows, and given the materials and with our geometry, we gave it a thermal zone, uh, chose a ground, and maybe included some shading. Then all we need to do is have a path to where we're going to send this file, and we have to run a simulation. And then we'll see what happens, and I'll talk about, give a little more context to this. Okay, so these outputs didn't change because I'd run this already, but what we have here then are outputs for four different HVAC systems, and we're comparing their, we have the typical heating, cooling, lighting, equipment, fan bar chart here, so we can see what percentages or what relative amounts of the energy loading is coming from those different sources. And then we have this nice little table here comparing the EUI for each system, its operational carbon, its annual operating costs, first cost, in other words, what it costs to install it, and then how large it is. And so then we can, by looking at this chart, decide which of these systems we want to use, at least at this stage in our project, and then come in and adjust the size of the system based on some parameters we'll talk about in a second. Before we do that, let's just go over. So uh, I'm not going to try to. I'm not summarizing these HVAC systems right now. I just want to make a couple points about them. VAV, and plus economizer, FCU, fan coil units with dedicated outdoor air supply, and VRF with dedicated outdoor air supply. What are these? So remember that HVAC systems, the most basic concept is that we have heating, cooling, and ventilation. So we could, the most efficient building we could build would be a box that had no windows and no ventilation. We could make it very energy efficient, but we wouldn't be able to live in it or survive in it. So we need both heating, cooling in most climates, and ventilation. So in a VAV system, which is a variable air volume system, uh, the these um, these three systems or these three components are combined together. So here we have an air handler that has coils coming to it from a chiller and from a boiler, so we can actually heat or cool the air. We have a fan that sends that air up into the zones. We have these VAV boxes that can adjust the amount of air coming in, so that would adjust the temperature of the room. And then we have returns where we're bringing the stale air back and mixing it with outdoor fresh air, and then starting the cycle again. So our heating and cooling is combined with our ventilation in one system. And so that's what we're calling VAV in this case. If we then add to that, this is a close-up of this box here. Um, if we add to that, so here's our outside air coming in, right? The fresh air here. So our outside air. If we have dampers, which can restrict the flow of air, and we have them controlled, electronically controlled, so that we can open and close them based on the outdoor temperature, or open and close them a certain percentage, then we can bring in more fresh air when the temperature outside is conducive to, for example, cooling. If we're cooling inside in large buildings, sometimes you're cooling even when it's cold outside. We're bringing in outdoor air, and then we can turn off the heating and cooling system and just, in this case, cool with the outdoor air, and so we're going to save energy. That's an economizer. So a VAV with an economizer would be this system where these dampers here were hooked up to controllers so that we were intelligently bringing in amounts of fresh air when the temperatures was conducive to creating the indoor temperatures we wanted. Okay, then the next one that's mentioned is a fan coil units. So the fan coil units in this case are these guys, and just think of them. They're just a place. They're the component which is making um, heating or cooling for the space. So creating the exact temperature you want in the space. And so you just see it's a fan. It's like an air handler basically, where we have a fan that's blowing across either something that's got uh, a cooling coil or some kind of heating coil. Um, and that can give us the exact temperature we want. However, we have separated these units from our fresh air intake, and so in this case, this giant thing up here on the roof is bringing in ventilation air. It's going through this big green thing is an energy recovery ventilator, so it's a big wheel in this case that is exchanging temperature and latent energy, which would be water vapor, between the incoming airstream and the outgoing airstream. So therefore, whatever temperature we've created in here, we're going to keep most of that energy as we exhaust this air through here, because we're going to transfer that temperature and perhaps some of the latent energy, some of the water vapor in or out based on what we need into this fresh air coming in, so that we're bringing in air that's very close to the temperature we need in the spaces. And so then these fan coil units are just tweaking the interior temperature to whatever we want in the given zone. It might be different here than over here, is the idea, right? Okay, so that's fan coil units with a dedicated outdoor air supply, which is this big thing. Then the final option that we have, so basically, in this little climate studio, or this grasshopper script from the climate studio people, they picked four different mechanical systems that we could choose in our basic early schematic design. Of course, that's not all the options. There are much more variations on even within these named types of HVAC, but it's a great beginning point. So the final one is the same dedicated outdoor air system supply, and let's just imagine that it's the same as this one, where it has um, fresh air supply and return. I think this is a slightly different system, but I'm just going to imagine that the on the other side of this is the exhaust. Um, and the difference here then is that we have a variable refrigerant flow heat pump on the roof instead of the fan coil units here. Um, we have a compressor on the roof, well, a system on the roof that is heating or cooling refrigerant, and sending that refrigerant to one of these units. And these are just three different kinds. So this is a mini split, a small unit, wall mounted. This is a larger ducted um, heat pump unit. And here's just another variation on that. So the idea being that we're exact same thing. We're bringing in fresh air. We're attenuating its temperature with this equipment here. And then we're getting the exact temperature we want in the different zones by sending different amounts of this refrigerant to the site. So in other words, there's not a fan here that's changing speed. It's actually just the amount of refrigerant coming that's determining the temperature in the room. All right, that's the summary really quickly. The point is then that these all have different characteristics, and they're going to be different in different climates. And so, for example, the VRF with DOAS is going to probably be usually the most energy efficient. It's going to have the lowest EUI, so that means it's going to have the lowest operating carbon. Um, but it may cost more to run. So you see here it's costing a little bit more to run than in this case than the fan coil unit with DOAS. Um, but it costs more to install initially. Um, Actually, in this case, it doesn't cost more than the fan coil. So this is going to change based on whatever parameters they're using here. But it is more expensive than these sort of more blunt systems, the VAV and the VAV with economizer. Um, and even though this is like a couple thousand um, dollars difference, and this is first cost, what it costs to install. Um, if we just had these numbers and not the rest of this information, definitely we're going to pick the cheaper system, right? Um, so it's important to have this information up front so we can have all the information we need or a lot more information than we would have normally had to make intelligent decisions before it's too late, before whatever our system is going to be as determined by other factors. Okay, so let's say then we say, I don't even know yet. I want to go check out some different, the different options over here. I'm going to delete this because we're just making an example here. And I'm going to turn on this little dot here. This is me where my roof mounted mechanical equipment's going to be. So now I'm going to create so we saw we determined the performance of the design. Now I'm going to um, lay out the geometry of it. So the first thing I'm going to do is select the point that I put on the roof. So you just need to draw a point that's coincident with your roof surface and apply it here to this B-rep or this component. And now you see we have this unit on our roof. And now I'm going to, well, we've already, let me get to where we can see this. I'm going to switch to wireframe. I'm going to come into my Climate Studio setup here, and I'm going to, oh, they were already turned off. So by the way, then, you may want to, the typical presets probably on, if you have Climate Studio set up for other things, are going to look like this, a little bit milky for this. So what I've been doing is just turning off a lot of the previews, maybe all of the previews. But let's just leave that as is for now. And then I can come down and I'm going to turn off, actually, do it here. I can adjust what's showing in from this model. I find that a little bit clearer just to at least explain this stuff. So anyway, so you have control over the visualization down here. And then we can just adjust these parameters of the system here. We can decide which one. So if I have a VAV system compared to a VRF with DOAS, again, this isn't the actual geometry. This is basically saying how much of the roof it's going to take up. So we can look at differences between the systems very quickly. And then we can come in and start adjusting the geometry of the ducting. So I notice, for example, this is wrapping outside. I'm not quite sure why that's happening. It has something to do with how I'm modeling this. But let's set a different duct offset from the exterior wall. And then I can, and by the way, so these ducts right now are sized based on our energy model, right? So this is basically saying this is the amount of ducting we need to move the energy required that was simulated in our Climate Studio thermal analysis, which is what we're doing with this. When we were up here, we're selecting options for a Climate Studio thermal analysis, and that's what we're doing. When we hit the simulations buttons, we're running the thermal analysis like we've been doing in other exercises. Okay, so then I can also adjust various parameters like the main supply duct aspect ratio. So the aspect ratio means the ratio between the width and the height, basically, of the duct. So do we want it long and thin? Do we want it rectangular? Do we want it tall and thin? And what does that do if we make an adjustment here? Then it's going to make it, like, for example, if I make it I'm making a fatter duct, right? So let me go back. So you see how, well, I'm sorry, actually, as I'm moving down on this slider, I'm making it fatter in the vertical direction, Z direction, but thinner in the width. And then if I were to equalize out the height that I had before, because it seems to do it from the center line, then what I'd be doing, let me just change to here, is changing the ceiling height. right? So even with the same system now that I'm looking at, if I change the aspect ratio, I'm going to change the ceiling height or the floor to floor height. Um, and like I said before, that might make a big difference in terms of my design, even at an early stage. So that'd be one reason I would do this right now. It's quick, it's easy, it gives us information for almost no time, which means no money in the professional world. Uh, so I think it's a good thing to do, and I would suggest you do it for your as a portion of your HVAC design for your final projects.